Hello, Honors Chemistry, and welcome to Chapter 13 through 13.7, where we are going to take the concept of solutions and layer in things we should be able to discuss at the microscopic level. So, for starters, here are some of the figures from your book that talk about what the act of dissolving looks like at the microscopic level, right? So here we have a giant chunk of sodium chloride, which, like we talked about before, is a network of ions all stuck together. We add that to water, and when we add that to water, it dissociates or ionizes into its respective ions, right? Which we know to be sodium ions and chloride ions, right? Now, what that also means, what it means to be dissolved, is it means that it must be able to interact with water. It must have a shared force of attraction, which, going back to things that you learned last year in biology, means that it must have a similar polarity, right? Polar things attract polar things. Non-polar things are attracted to non-polar things, right? And you guys learned that water is among the most polar substances. So things that are very polar dissolve very well in water. And thinking back to what you learned about bonding in 8th grade, right? Ionic compounds are really just super, super polar, right? So polar, in fact, that they give electrons instead of sharing them. All right, so if we take a look here, right, at the second figure, it shows the direction-oriented dissolving of an ionic compound in water. So you'll see that here we have our hydrogen ends, which are the positive end of water. So the hydrogen ends, which are the positive end of water, find themselves oriented toward the anion. Yes? The positive hydrogen ends of water are oriented towards the negative ion, where the oxygen negative end of water is oriented toward the cation, right? And that's always how it's going to be, right? Of course, the cation and anion can change depending on the compound, but that's always how it will look. An ionic compound will look when dissolved in water. When we think about macroscopically, right, obviously, if something is dissolved in water, it means it's a homogeneous mixture, which means that to our eyeballs, right, we can't tell that there's anything in anything. It looks like one sample. All right, going to electrolyte solutions. This is something we already talked about earlier this year, but just layering on how that applies here, right? If we have dissolved ions, so if we have an ionic compound that happens to be soluble in water, which goes back to your solubility rules, if an ionic compound is soluble in water, it's going to dissociate into ions, which makes it an electrolyte solution, where electrolyte solution simply means that it will conduct electricity. Obviously, there are a whole wealth of molecules that dissolve in water. Molecules being molecular compounds composed primarily of CH and O that also dissolve in water, right? Sugar molecules, lots of different types of sugar molecules, especially if you think back to biology, that dissolve well in water. But because they're not ionic, and we know that because what? Right, when we look at the makeup, it's not made of a metal and a non-metal, right? So it's molecular, which means that when it dissolves in water, though it's polar and it's able to interact with water, it forms a non-electrolyte solution because there are no ions formed, okay? All right, quick reference to this graph for solubility. Note that this is grams of solute, right? So this is how much solute dissolves in a fixed amount of water based on temperature, and clearly as temperature increases, right, solubility increases. All right, solubility of gases, right, this is something we all have a little bit of life experience with, right, going back to sodas. When we say that there is high pressure, right, and we'll talk about this more when we get to the unit on gases, right, but when we talk about high pressure, what that typically means is there are more gas molecules in a fixed space. And if it has a higher pressure, that means that there are more collisions with the surface of the water. If there are more collisions, there are more opportunities for the CO2 molecule to interact with the water molecule in such a way that the CO2 will dissolve. CO2 is nonpolar, so the dissolving isn't very good, but they can dissolve temporarily. And we know it's temporary because we've all, I assume, had the experience of opening a carbonated beverage and forgetting about it and coming back a few hours later and realizing it is definitely not the same. Now, let's talk a little bit about molarity, right? That's obviously the big conversion factor for this unit, right? Where molarity is one of the neat conversion factors that gets its own symbol, right? But every time we see that symbol, we should think to ourselves, ooh, molarity, and then we should rewrite it as its two separate components. So, for example, if I have a 0.1 molar NaOH solution, right? What that means is that there are 0.01 moles of NaOH solute equal to 1 liter of NaOH solution. Yes, where aqueous means solution. So 0.1 moles of solute per or equal to 1 liter of NaOH aqueous, right? And that's how we get molarity, right? Now, and it works just like density, right? Where density is grams per, let's say, milliliter, right? And in order to solve for density, I would need a mass and a volume, and I would divide the two, right? But if I have the density of something, I can use it as a conversion factor between mass and volume, right? Molarity is the same thing. If I know the moles and the volume, I can solve for molarity. Or if I'm given the molarity, I can use the molarity as a conversion factor between moles of solute and the volume of my solution. Yes? All right. Okay, now we're going to calculate the molarity, which means that we need moles and liters, right? By putting this many grams of sodium nitrate in a beaker and diluting it to this volume, right? So here is, oh, there should be a unit there, right? So this is obviously the volume. This is a mass. Do we have moles? No, not right in front of us, but we are capable of getting to moles, right? So we're going to take our 55.8 grams of NaNO3, and then we need to do what? Right, we're going to figure out the molar mass so that we can then convert to moles. And then, now we've got moles, now we're going to go ahead and, how you want to format this is up to you. I'm just going to say 1 over 2.50 liters, right? Now if I look at my units, right, I have moles of that over volume of my solution, and then I would just do the math. And then we would round to the proper number of sig figs. And whether you want to use that or this symbolism, moles per liter, is up to you. Doesn't matter. Same thing, right? Likewise, we could just stop at the 55.8 divided by 85 and take that answer, which is the 0.65647 moles. Here it's important not to round too soon because we don't round to the very end. We could take that number of moles and just divide that by 2.5 liters if that's what visually makes more sense to you. Do this, right, which would give us that same answer, right? So if you want to do it in 2 steps, that's totally fine, right? You could stop here and then just do that. Next up, it says how much of this contains that much grams of KCl. So obviously this is our given, right? And I need to know how much of that, and here that means a volume. And we know that because this is a solution, right? This is an aqueous solution. That's what the M stands for, right? Aqueous solution, which means that we must be looking for a volume, right? That's our question, right? So let's go ahead and get started. And we'll note that this is a KCl solution, and we're talking about mass of KCl, right? So 55.8 grams of KCl. And then obviously we need to get to, right, we need to get to moles. Now we're going to employ that. And again, so like I said, let's take a minute and rewrite that so we're likely to use it correctly. 2.55 moles of KCl is equal to 1 liter of KCl aqueous, right? So we're going to put the parts where they belong. So 0.225 moles of KCl per every 1 liter of KCl aqueous. And then we'll just do our math, right? Check our units. And then we just type everything in. And so what this says, right, is that if I need 55.8 grams of KCl, I would need 3.33 liters of my aqueous KCl solution. Yes, as in that volume of solution contains this mass of KCl. All right, next up, determine the molar concentrations, right, so that means molarity, of calcium ions and chloride ions in calcium chloride, right? So here, I want to know the pieces of the calcium chloride. So let's write some relationships between calcium chloride and its pieces. I know that 1 mole of calcium chloride is equal to 1 mole of calcium, 2+, and I know that 1 mole of calcium chloride is equal to 2 moles of chloride ion, right? So then if I take my 0.75 moles of CaCl2 per every 1 liter of CaCl2 aqueous, then I know that 1 mole of CaCl2 is equal to, let's say, 1 mole of Ca2+. Those cancel. And then I'm left with moles of calcium ion per liters of solution, right? And that math is real simple, right? Should be. Molar Ca2+, right? And then obviously, it's it's not a big stretch that this next step would then just say 1 mole of CaCl2 for every 2 moles of chloride ion. And then this would be double that, which should be 1.5 molar chloride ion. Yes? All right, one last one. So how much, so again, volume is our question, of this solution should we use to make this much of that solution? What's happening here? Right, this is a dilution, right? So we would like to know volume, right, of 6 molar. So basically this is our 6 molar, and we're going to dilute it down to that. So 6 molar diluted to 0.585 liters of 1.2 molar, right? So, and we know it's a dilution, or it should be clear that it's a dilution because it's a sodium nitrate solution and still a sodium nitrate solution, right? Which is different from what we're going to talk about next period. Okay, so anyway, we should see that, and we see all our pieces set up now. So let's go ahead and do our M1V1 equals M2V2, right? So M1 is obviously 6 molar. V1 we don't know. And M2 is 1.2 molar and 0.585 liters, right? And then we would just solve for our V. Yes, does that make sense? And this is all this question is asking of us. All right, thank you for listening. Be good, and I will see you soon. Bye.